you have the picture in the head. If I say lim sup xn is equal to lambda, then you have to have this picture in your head. Here is somewhere lambda. Here lambda. So then you take any epsilon, that is according to the book, this is not lambda. L plus no. L plus, so I write just say L plus epsilon according to loop, that is your x, right? So, and here again he says x, but let's say this is L plus minus epsilon. What you need to have in your mind is that now epsilon is given, no? Epsilon is greater than 0. So as soon as you are given, you get an n here. Capital N, all the terms are below this line. Buffalo, New York, everywhere. But just because it is below this line, it cannot go forever. Somewhere it has to come above this line. L plus minus epsilon line. Again, however, now you cannot go above. Now, you don't have to stay here forever. Then you cannot go above. So, there must be some here, greater than L plus minus epsilon. So, the graph will be like, before capital N, we don't know anything. It can be going like this, but after N, it is like this. You go here, come up, but cannot go above, like this. So, there are many points going above this line. But after capital N, all of them are below this line. That is lim sup. Lim means the similar thing. Similar, actually, the other side. If you turn the graph by 180 degrees this way, then you get the graph of lim nymph. So this is the idea you need to keep in mind. Given in epsilon greater than 0, there is an integer n. After that, it is all graph is xn is below that line. But it cannot go all the way to hell. Why? Because given any n at the bigger n, it has to go above L plus minus epsilon line. Now, however, it cannot go above the L plus line because capital N is here, below here. So if I write in my words, without using x, lim sup xn n going in equals L plus, if, actually this is if and only if. For each epsilon, let me say Roman 1, for each epsilon greater than 0, for each epsilon greater than 0, there exists some integer n. Because of that dependence, I will write n epsilon such that for each simple n greater than n epsilon, xn less than lambda plus epsilon. For lambda plus epsilon, he has used
L plus epsilon.
yeah, always. I go for That's the letter I use. So this is one condition. The other one is and. Good. For each epsilon greater than 0, again I have to write them because of the way. That doesn't matter. I am repeating, no? Because I should have written for each epsilon greater than 0, then 1 comes here, then 2 comes here. That's better way of writing. For each epsilon greater than 0, for each simple n belongs to, say, Z plus, there exists simple n greater than n. Simple n belongs to Z plus and simple n greater than n such that Xn m here greater than L plus minus epsilon. This is, he doesn't use epsilon, but he uses X. This is the picture. So it is above L plus epsilon, sorry, it is below L plus epsilon line, but it cannot be close to L always, it has to come above this thing, but cannot go above, go down. You get the picture? That is the meaning of Lim-Suk from a picture. That is how I write. I don't use X because in the analysis course, better to be familiar with L plus. So if you have this idea in your head, most of the parts will be clear to you, but his definition is that he get any tail, every tail, get the soup, it is decreasing sequence, its limit is his Lim-Suk actually, since it is decreasing, and of course bounded below, limit is the infimum of monotone. There is something, I don't know, if a sequence is decreasing, it converges, and bounded below by the way, it converges to inf of the set of all xn. So that is the thing. So if you are using this idea, I mean, he has all those things are in the line. Because you know, the reason is that when you want to solve the problems, you have to have a feeling about Lim-Suk, Lim-Dif, inf, co-sequences, this and that. For instance, if you are going to do part D of the theorem, this is on page 144. Let me go back and see. I can do that. What should I do to go back? Any limit point of A, then we have L minus less than or equal to C, less than or equal to L plus. So we have to do two things here. Any limit, if C is any limit point, then C greater than or equal to L minus, we have to do that. Again we have to do that, C greater than or equal to L plus. It is a limit point. So what is in your brain about limit point? If C is any limit point, what do you know? The idea I am asking about. What do you know about C and Xn? If I say C is a limit point.
So you choose any capital N. So there must be another integer simple N such that it's always very close to C.
Simple N. What else? You said if you choose any capital N, there is a simple N.
Yeah, which is greater than capital.
Greater than capital N, and Xn is very, very close to C. So, but that's true, but to the contrary, in Sri Lanka, for instance, to many people, somebody who is white, when we say white, I mean he's fair, it's beautiful. Because I had a friend, his name is William from India. One day we were having a chat and having a cup of coffee. He was saying, Rama, all the American girls are very beautiful. No? This guy is married. No. Manga, why on earth you say that? See, everybody is white, no? But of course there are very beautiful girls over there, but everybody, that's not true at all. Some are actually real ugly. I mean, even in this country that's the case, no? In any country it is true, so you cannot generalize. If C is any limit point, then we have to prove L minus less than or equal to C and C less than or equal to L plus. So I guess I am kind of proving everything. So but the reason I am doing is that because you have to have the idea of lim sup as well as lim as well as limit and sup and inf. These are the analysis. Analysis is all about lim sup, limit, sup, inf. That's it. Nothing else. Nothing else in analysis. Sup, inf, lim sup, limit. Then other than that you get sequences. No? Okay, so suppose you want to prove this thing. Suppose for sake of contradiction, actually I am not doing homework, but I am trying to convince you. Because to many people, when you say lim sup, oh, this is very difficult. That's how they think. Suppose for sake of contradiction, C is strictly greater than L plus. Now let epsilon greater than 0. I am not writing the proof but showing you. I am going to go to the diagram. Because analysis is about graphs. No? These graphs are discrete. No? Then you get continuous graphs. Fx equals x graph, fx equals absolute value x, fx equals sin x and so on. Now, this pen is also. So let's go to the graph. I have written C greater than L plus. I am assuming. Suppose that's like that. So let me draw. Here is L plus. Now I will, to make the graph, finally I will put C a little bit upstairs. Right? So I am assuming C greater than L plus. Now I have given epsilon. No? So let's, for the time being, assume epsilon is, assume this L plus epsilon is strictly less than C. That means epsilon less than C minus epsilon. Or else you can say, I should not say everything, then you will copy down. Okay, so what I am saying is this is my this thing. So, because of the lim sup graph, I know after some capital integer n, all the terms are below this line. All of them. Now can you see, can you have anything very close to C? Nothing. Contradiction. That's the rule. Right? That is the rule. Similarly, if you assume L, what? C is strictly less than L minus, you get same kind of contradiction. Limit point is, there are infinitely many points very, very close to C. When it is lim sup, if you are given epsilon, all the points are below L plus epsilon after some integer. This cannot happen. If this cannot happen, C must be less than or equal to L plus. That is the proof. So you have to, you cannot say now insufficiency something. Isn't it easy? It's easy. It's not difficult. But anything can make difficult, no? By the way you one writes. Sometimes some lecturers in this country, they make the subject they teach very difficult. They try to give an impression, oh my gosh, I am the best in the world, even better than Terence Tao, you know. They are impressions. Okay, now actually I have done many of these things. So you try to write very logical and precise statements. Take your time and write. But I can say take your time, but you are doing many other things. I know that. However, this is the thing. If you are good in analysis, then you will find algebra very easy. That will happen because here, because of this epsilon, delta, rational, irrational, this and that, life is very difficult here. Over there, discrete, no. Any group, are you given the definition of group? So it has only 3 axioms, no? Actually, one can say you have an unempty set, you have a binary operation, circle or something, no? First one says circle is associated. That's how we deal. Then the second one says identity. What is the other thing? I forgot it. Inverse. This is sort of, there are different ways of defining this thing. And it has every element has an inverse. From that, can you imagine in a way, somebody is doing certain things for the PhD because of these 3 lines? But only 3. That's all. Based on that, you say this and that subgroup, nilpotent group, you have come to these terms. Sooner or later, you are coming to that. It's very discrete. I'm not saying it is easy, but in comparison, must be easier, even though I shouldn't say so. Alright, so now limbs of draw graphs, always you have to have this picture in your head about limbs, and you need to draw this similar picture for limb. Inf, then it will be easy. If you cannot prove directly, always go for the contradiction. That's why they say in Sinhala, Kokatattaile. Okay, now, where are we? I told you I will give a problem per week from me.
Yeah.
Okay, let me give that. Prove that. This is the problem. This is very easy, but the reason I am giving and grading your, not grading, I am looking at your answers is because I want you to write precisely. That is how you see mathematics, by writing. Without writing, you don't see it. Okay, do that. P, R, O, V, by V and R both are same, you do by now. Prove that. Let action, let's say, let action be a sequence. I write this way always. Be real sequence. Prove that if limit is C, then me writing my language. I always could use simple as if you catch the correct way of writing, then where it leads you to mathematical thinking. As long as you don't write precisely, you will find it difficult. Okay, that is enough. One problem per week. Or 2 problems every day, 1 problem, something like that. Okay, now let's go to actually this you are taking a statistics course, no? So xn is a random variable which converges well. Then average of xn also converges well. So that is used in statistics. Where are we? I cannot read.
No, squeeze test after.
So you know squeeze test now, no? Oh, we did not know this one. It's a very important one. Every Cauchy sequence converges. No? I guess that's it. That's the place where I said I didn't want to rush. Okay. This proof is very good. This proof we can understand. So I'm not going to write. Let's go through this. Already tells us that every convergent sequence is Cauchy. So it's supposed to show that every Cauchy sequence is convergent. That's what we are going to do. Let's read it. My throat is bad. I don't know what. I was kind of outside my home and it was raining a little bit. I got but some effect from the rain. Okay, let n being a Cauchy sequence, we will prove. We know from lemma 5.1.15 what precisely from the extension of this lemma to the real numbers, which is proven in exactly the same fashion, that the sequence n is bounded by lemma whatever. So what it says is every co-sequence is bounded. No, you can prove it. This implies that L minus and L plus of the sequence are both finite, right? That we know. Is that clear, Buddha? Right. To show that the sequence converges, it will suffice by proposition to show that L minus is equal to L plus. Because somewhere in that theorem, it says A converges to C, part F actual by the way, that main theorem, then we must have L plus equals L minus equals C. If xn converges to C, actually if and only if L plus lim sub and lim min both are equal to C. Proof of that also, you draw a picture of this. Picture is the proof. But the thing is, like some mathematicians, they say, oh, especially people in algebraic topology or differential geometry, they always say, oh, take the torus, spend this, like that. I mean, we cannot afford to do it here. But by very important, however, when you are going to do big research, you have to accept the fact that there are many other research papers. So you read if you are going through what is in every research paper, then you will take, I guess, 100 years to do a PhD. So you have to have the ability to take it for granted. So people in algebraic topology, that kind of areas, they are extremely good at accepting it. Analysis people, they find it difficult. They want to see the proof. So it is a disaster for analysis people. So I am going to assume that you have done it. And you draw the picture of here, if A n converges to C, draw the picture. That picture itself says L plus L minus both are equal to C. But you have to be able to write. why do you say, but pictures helps you. However, you know this statement in English, looks are deceptive, no? Somebody may look very kind, but can be a killer, no? Okay, so now we are going to prove that L minus and L plus both are equal. Let's see, every Cauchy sequence. We are going to prove that every Cauchy sequence converges, no? Now let epsilon greater than 0 be any real number. Since A is Cauchy sequence, it must be eventually epsilon is steady. What it means is that that is given not already epsilon is given. No? For each epsilon greater than 0, there is an integer capital N, such that for each n greater than n, an, distance between an and whatever the with an and am and m are larger than capital N, absolute value of xn minus xn is less than or equal to epsilon. No? That's the meaning. There it is an n greater than or equal to 1 such that a is epsilon is steady. In particular, we have an minus epsilon less than or equal to an less than or equal to an plus epsilon for all n greater than or equal to n. This is true for any n and any m. But he is fixing capital A n here. So, what this says is an minus absolute value of an minus a simple n minus a capital N less than or equal to epsilon. That's the meaning of it. Then he says by proposition 6.3.6 or lemma 6.4.13, I suppose that is a homework. It's exercise, no? I guess you must have proved it. By the way, I forgot to tell you, that is also a very important exercise. Lemma 6.4.13. Very important, prove it. And take it to your blood. After proving it, you must be able to take it for granted, like, many mathematicians. I told you, some of my batchmates, not batchmates, my fellow colleagues, I mean, they cannot do a simple thing, but they take everything for granted. Yeah, that's a difficult quality. Since simple a n less than or equal to a n plus 1, this is he is using from lemma 6.4.13. If a n less than or equal to this number, then lim sub a n also less than or equal to that number. Clearly, lim sub inf less than or equal to not this lim sub, he has writing inf and sub according to the definition in the book. No? Actually, he could have written this thing at once, cannot he? 6.4.13 lim sub a n less than or equal to doesn't matter, but if a n less than or equal to something, you can prove that lim sub a n also. By the picture it is real. By the picture. Suppose a n less than or equal to lambda somewhere here. All of the a n are less than or equal to lambda. Then lim sub L plus cannot go above, because you can choose lambda minus L plus divided by 2 as epsilon. So somehow he has taken 2 steps. It's not wrong, but anyway, so that line is clear. What he says is that if a n less than, if a set is bound, a sequence is bounded above by 5 Supremum also bounded by 5. But write the proof. Always I am saying write the proofs of very little things. That will make you learn how to write proofs. So that's why that thing is correct. Inf is always less than or equal to sup. And hence by definition of L minus and L plus, then you get that line. Right? Because lim sup is, if somehow he says proportion 6.3.6 again, I'm not going to look at that. Then you get somehow L minus less than or equal to L plus. I suppose I proved it that day. See, I am proving everything from the picture. In the sense, I am getting the idea from the picture. But you know, you have done O-level geometry, if you draw a false picture, you can prove things which are absolutely rubbish. So then you get L minus less than or equal to L plus, and both of them lies in between A plus epsilon and A minus epsilon. Therefore, L plus minus L minus must be less than or equal to 2 epsilon. No? That's clear. What he says is here we have A minus epsilon, A minus epsilon, here is L minus, here is L plus, here is A plus epsilon. What he is saying is this distance is smaller than this distance. This distance is L plus minus L minus. This distance is 2 epsilon. Right? That's what we have to do. Now actually we are done, but this is true for all epsilon greater than 0, and L plus and L minus do not depend on epsilon. So we must therefore have L plus is equal to L minus. Right? Is it clear? Otherwise, if you, very beginning, if you wanted, you could have assumed that L plus, you could have chosen an epsilon, L plus minus L minus divided by 2 or something. Then you will end up with the contradiction. So anyway, here he says it. If L plus greater than L minus, then we could set epsilon equals L plus minus L minus divided by 3. Then you get the contradiction right away. So now this is a very good proof. Actually, this is the only proof for this fact. We know that every convergence sequence is Cauchy. That is easier to prove. But this side is difficult. Every Cauchy sequence converges. That is called the completeness of real number system. Because if you take this rational number set, there are Cauchy sequences in rational numbers, but their limit is in real numbers, limit is in irrational numbers. So, set of all rational numbers is not closed, but set of all real numbers, yes. Okay, we proved that, but we are in a different place today, no? Where are we at? I cannot remember. Can you remember it? I passed the place?
No, a little bit up. So I'm done with the proof now. So from remark 6.1.
That day we stopped at the proof, right? Now is it very clear? I mean, absolutely clear. When I asked, is it clear? I mean, I told you, there was one girl, girl, she is beautiful in my lesson, I was doing menstruation. Lecturers come and teach, we don't understand anything. This girl says, she is from Brahmana caste. Indians are very serious about the caste. No? So she is very proud. Actually, she didn't talk to many of our batchmates. Yeah. And she was helping us. Our lecturer says something. We don't understand. Well, lecturer thinks that she understands it. No? That's the escape route for lecturing. Oh, she understands. So let me continue. However, when the results came, she failed. Others he proved the thing. So I'm not going to, I guess, read this paragraph because he says metric spaces, you don't know anything about metric spaces. Doesn't make any sense to talk about it. Some standard limits, by the way, this is the important one. You need to know some standard limits. Armed with the limits, laws. The limit laws and the squeeze test. The squeeze test is a very important test. We can compute a large number of limits, he says. A particular simple limit is that of the constant sequence C. We have, if the constant sequence, for a constant sequence, if the constant is C, limit of the sequence is also C. Very easy to prove, no? Very easy to prove. Then he is proving we have limit 1 over n divided by I don't know what to do this. I don't know whether this will come again. As a result, I why did I stand? It's that. Why should I look at the book again? Look at the board. 1 over n raised to the power 1 over k, he says. Limit of 1 over n is equal to 0, we know that. For every integer. Limit of k is an integer here. In the sense. I don't think so. This is not true. The way he has written. Because if k is a negative number,
Every k greater than 1.
Greater than or equal to. Okay, these are observed. Limit n tends to infinity. This is equal to 0. We have shown this result for k is equal to 1. Limit of 1 over n is 0. I guess he is proving it. He is proving that 1 over n raised to the power 1 over k is a decreasing function of n. No? K is fixed here while being bounded below by 0. Right? That is clear, no? By proposition whatever, for decreasing sequences instead of increasing sequences. I guess the results was proved in the book for increasing sequence, but similarly it is true for decreasing sequence. We should know that this sequence converges to some limit. If you take a sequence xn greater than or equal to 0 for every n, if it has a limit is also greater than or equal to 0. Since this is decreasing and bounded below, it has a limit. That limit also must be greater than or equal to 0, right? Can you prove all of the what I am saying? Because I may be good at telling you and running away. Do you understand? Can you see that 1 over n raised to the power 1 over k is decreasing? Can you prove it? What is the meaning of decreasing? The sequence is decreasing.
All if like so all the no, an is always less than an plus 1 for each n.
Is he right?
No, an is greater than an plus 1. It's like going down.
Okay, so if when n increases, n plus 1 also increases, same thing. No? So, because of what you said, this is decreasing. You understand it, no? You can prove it. Because what you are saying is, we know that n plus 1 greater than n. Therefore, n plus 1 raised to the power 1 over k also greater than 1 over n raised to the power 1 over k. Therefore, 1 over n to the 1 over k greater than 1 over plus 1 raised to the power 1 over k. Right? So it is decreasing. Certainly bounded below by 0. So it has a limit. Actually, limit is the minimum of this sequence. So he says L, he is putting L equals limit of this sequence. Raising this to the kth power and using the limit laws, we obtain L to the k L to the k is equal to limit of 1 over n. Because we have in the particular theorem I was discussing yesterday, if an converges to L, an squared also converges to L squared. An to the k converges to L to the k. You can prove it by induction. So he is using that result. If 1 over n raised to the power k converges to L, kth power of that converges to L to the k. By induction we can prove it. We thus have L to the k is equal to 0. Then L must be equal to 0. So that's the proof. Right? So this is the result that you need to remember. That's why he is doing it. That's why he is doing it. Now, next one is also very important. Let x be a real number, then the limit of x to the n exists, always exists, which is n is equal to 0 when mod x less than 1. If mod x less than 1, limit of x n tends to infinity, x to the n exists and it is equal to 0. Exists and it is equal to 1 when x is equal to 1. If x is 1, x to the n is 1. So constant sequences converges to the respective constant. And diverges when x is equal to negative 1 or when mod x greater than 1. Because if he is using here, I will not do it, I would like you to do it because these are not that difficult. If x is mod x less than, suppose x is positive, for instance, here is 0, here is 1, here is x. Then let's take a number like 1/2. 1/2 squared is 1/4. Can you see? 1/2, then squared is 1/4, then 1 over 8. No?
Yeah.
1 over 8. It's decreasing. This is true for when x less than 1. However, greater than 0. 1/2 is such a number. So you can prove that if x lies between 0 and 1, x to the n is a decreasing sequence which is bounded below by 0. So it has a limit, and limit also will be 0. I will not prove it because I would like you to prove it. And of course, if x is 1, it is the function sequence, it converges right away to 1. If x is equal to -1, then you get this sequence, -1 plus 1, -1 plus 1, -1 plus 1, like that. This sequence does not converge because no matter how far you go, terms won't get close to any real numbers jumping from -1 to +1. That is clear. However, let's see what happens when x greater than mine. When I will erase these because these are there. Here you have the line, here you have -1, here you have +1, over here you have 0. So if you take any x here in this part, if you take any in here, you have shown that limit of x to the n is equal to 0. And then when you take -1, diverges, here converges. Now if you take a number like -2, what will happen? First term is -2, next term is +4, -8, +16 and so on. So if you, when you draw the graph, what will happen? First term is -2, next one is 4, -16, -8, +16, like that. It's going to heaven this way, and it is going to hell also. Yeah. So definitely it will not converge. So, but you have seen it, but you need to be able to write precisely. Very important. Before another 2 or 3 months' time, you must be able to write a proof. And in the sense that, now he gave me a solution to 2 problems. His mathematics is correct. His solution, the way he has written, is not good. I mean, it is, I'm not saying it is wrong. So you have to learn. Again, you should not write not unnecessary things in the proof. Because it makes the proof ugly if you write unnecessary things. Okay, what else he says? Next one, for every x greater than 0, x to the 1 over n is equal to 1. This is kind of a little interesting. Last one. Because if you take a number x greater than 0 and x to the raised power 1 over n, when n tends to infinity, 1 over n tends to 0. So this is kind of like x to the 0 is equal to 1, something like that. But you cannot write like that. You need to do it. So I will not give you the proof. It's good for you to do it alone. So this, you must, the things here 6.5.2 and 6.5.3 is a must. If by any chance when you do homework you don't, though you write a proof, if you don't believe it, ask me to prove it on the board. Because these are very important exercises. Some exercises in this book, in any text are not that important. But these two are very important. Especially the 6.5.2 and 6.5.3. Because this appears like x to the 0 equals 1. That's good anyway. There are exercises here, let me read. And I guess I read it into the cube greater than 0. That's no problem. Prove lemma 6.5.2. That's no problem. Lemma 6.5.3. Yeah, it's not obvious. 6.5.3 is not obvious. You have to do some little bit of work somewhere. Okay, so I guess we finished the limbs of elements chapter. By now, I think you must have an idea about limb sup and limb inf better than any university student. I will make it even better after this whole thing. I will say, this is how I define limb sup and limb inf. Then you will be as good as anybody in the world. But now these I am proving you. So you have to prove. That's why I say, you write the proof you really believe. Proof is such a thing. Now you say 1 plus 2 is equal to 3. Nobody can argue with you that no, it is not 3. So proof must be such a thing. You must really believe it. Okay, let's go to subsequences. That is very, very important. When you talk about sets, you have subsets. When you have talk about sequences, you have subsequences. So let's see how I have spent time. Let's read the thing he says. I guess now after chapter 6, it's better than first 5 chapters. Again, have a next chapter. You go. I don't know. All right, Putta, let's see subsequences. This chapter has been devoted to the study of sequences of real numbers and their limits. Some sequences were convergent to a single limit, while others had multiple limit points. No? That is true. For instance, -1 to the n sequence has 2 limit points and they are
-1 and
-1 and +1. Very good. Sequence 1, 2, 3, 1, 2, 3 does not converge, but it has some limit points. What are they? 1 and 2 and 3. So that's the idea you have to have. Rigorous writing should come after very little things that you are absolutely convinced. Then you can stand on firm foot. Alright, I hit the ground, my shoes. Okay, for instance, the sequence here 1.1, 0.1, 1.01 and so on has 2 limit points. You can see some terms get very, very close to 0, some terms gets very, very close to 1. Okay, but it's not actually convergent, we know that also. However, while the sequence is not convergent, it does appear to contain convergent components. Because if you take, for instance, -1 +1, -1 +1, if you take only the -1 terms, it converges to -1. If you take +1, it converges to +1. To make this notion more precise, we need the notion of subsequence. I mean, this is how it is defined. Let an and bn be sequences of real numbers. We say that bn is a subsequence of an. I am on page 149, it is on the board also. We say that bn is a subsequence of an if and only if there exists a function fn to n which is strictly increasing. Very important. That is fn plus 1 greater than fn for all n belongs to n, such that bn is equal to a fn. So what? Now I will erase this because you don't have. Is this also? You have a sequence. A. Let's say he goes from 0 to infinity, doesn't matter. Then he has another sequence B. Bn is n going 0 to infinity is a subsequence, like supposed to be. I wrote P because I said supposed to be subsequence. If what he says is there exists a function f there is and increasing. The function is like this, silly. So f from n to n. Such that, I write it such that. Such that what? F is strictly increasing. This word is very important, strictly. Increasing. And Bn is actually AFN. In other words, say, suppose you have a sequence A0, A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, A11. Like this, then he says Bn is f is an increasing function. So maybe this is your B0. Then B1 must be a bigger integer than 2. You cannot go back. So maybe this is your B1. B1. Okay. Then B2 must be somewhere here, right? Because f is increasing. This is your B2. Like this. So B0 is A2, B1 is A5, B2 is A8. Actually, f of 0 is 2. F of 1 is 5. F of 2 is 8, increasing. That is the definition. Yes.
So it could be B0 can be equal to A0 is also right.
Of course.
But sir, here says that f of n plus 1 is strictly greater than f of n.
Yeah.
So 0.
So it's not a contradiction. It doesn't say fn needs to be bigger than n.
I did not understand your question. If I would be 0 here, what is the problem? That will be the problem.
If it's an increasing function.
Yeah, so that's why 0 is equal to 0, 1 is 5.
Which means
He does not say Bn is strictly greater than n. He doesn't say such a thing. Of course, what he is saying is Bn is strictly greater. Suppose I write a sequence like this. B0 is equal to 0. Let's see whether you have an notation. B1 is equal to 5. B2 is equal to 8. Then I have my function f of 0 is equal to 0. F of 1 is equal to 5. F of 2 is equal to 8. Is that a problem? It's increasing.
which means the whole function should be increasing the
F is an increasing function. F is increasing. I'm correct, no?
Yeah.
F is increasing. Yeah, f of 0 is equal to 0. Now f of 1 must be greater than 0. That's the only thing. F1 is 5, F2 is 8. Like that. That's why another way of finding subsequences, you cross some of the terms. No, sorry, I crossed the word. Silly guy. Somehow my throat is bad. I cross this term, this term, this term, this term, then cross this term, then I cross this term, this term, this term. What remains is a subsequence, increasing order. That's the thing. So it's very clear. But there is a funny thing, however. Now, if you take a set, if A is subset of B and B is subset of A, then they are same. If An is a subsequence of Bn and Bn is a subsequence of An, they don't have to be equal. I hope he's given us an exercise. 6.6.2 exercise on page 152. Page 152. Question number 2. Can you find two sequences An and Bn which are not the same but such that each is a subsequence of the other? An is different from Bn, but An is a subsequence of Bn, Bn is a subsequence of An, but two different sequences. So you cannot generalize the idea coming from sets. If A is subset of B, B is subset of A, then A and B are equal. No? Even for real numbers, if A less than or equal to B and B less than or equal to A, then they are the same. No? So this is different. This is not difficult. That's why I say always do easy problems, don't do difficult ones. Because if you do difficult problems, you get tired mentally. What is this? I don't know this. Leave the difficult problems for the end. You do easy problems at the beginning. Okay, where am I? So here is just the definition. Yes. Okay, example 6.6.2, he says An is a sequence, then A2n. Can you see on page, I guess, let me put it. Can you see An is a sequence, then 2n, the sequence 2n is an increasing one. Therefore, A2n is a subsequence. Then Fn equals 2n is a strictly increasing function. Note that we do not assume F to be bijective. There is something like that. All we need is increasing part. Informally, the sequence A0, A2, A4, A6 is a subsequence of A0, A1, A2, A3, A4. Suffixes must be increasing in the subsequence. That's all. That is all. Here he says example 6.6.3, the two sequences 1.1, 1.01, 1.001, then 0.1, 0.01. By looking at this, you cannot see it. Is mentioned earlier, are both subsequences of 1.1, 1.0, 0.1, 1.01. If you look at the 1.1, if you look at this one, 1.1 is the first term, then 1.01 is the third term, 1.001 is the fifth term, increasing. Again, in this one, other one, 1.1 is
0.1.
0.1. 0.1 is the
Down there.
yeah, okay. Silly guy. 0.1 is second term. 0.01 is fourth term. Increasing. That's all. No big deal. The property of being subsequence is reflexive and transitive, though not symmetric. Okay, so let's read it, that's not difficult. Let A, N, B, N and C, N be a sequence of real numbers, B and B sequences of real numbers. Then A, N is a subsequence of B, N, subsequence of N, A, N equals 0 to infinity. Furthermore, given sequence, when it comes to set A capital, if A is a set, A is subset of A. Like that, if A n is a sequence, A n itself is a subsequence of AN, that's what it says. Furthermore, if BN is a subsequence of AN and CN is a subsequence of BN, then CN is a subsequence of AN. That is also very clear. I mean, it is like here. Here. Now I have this one. AN, then I cross out some of the terms. What is left over is subsequence. Then I am going to write that A0, A5, A8, A12, A13. There are some more terms and I have written after 13. Then I cross out some of the things from here. I cross out this guy, this guy. Then what you get is A0, A8, A13. Increasing of 0, 8, 13. That's what this theorem says. No big deal. Subsequence of a subsequence is the subsequence of the original sequence. That is clear. Okay, this is a good result, proposition 6.6.5. What this is subsequences related limits. Let A and B be a sequence of real numbers and capital L be a real number. Then the following two statements are logically equivalent. The sequence A n converges to L. Every subsequence of A n converges to L. That is very easy. No? If A n converges to L, what this says is far away, both terms are arbitrarily close to L, I guess in better English. Far away terms are arbitrarily close to L. You take a subsequence, again, far away terms must be arbitrarily close to L. No problem. So, if the sequence A n converges to L, then every subsequence of A n converges to L. However, this is if and only if no. If every subsequence of A n converges to L, A n itself is a subsequence of A n, so it must converge to L. That's the proof. You understand? So, both are easy. Now what? Subsequences related to limit points. Yes. Okay. Subsequences related to limit points. Let A and B a sequence of real numbers and let capital L be a real number. Then the following two statements are logically equivalent. What is here? You have A n is let A n be a sequence of real numbers and let capital L be a real number. Then the following two statements are logically equivalent. L is a limit point of A n. There exists a subsequence of A n which converges to L. You can imagine the proof, no? By looking at the picture. L is the limit point of A n means there are so many points very, very close to L. So, among the points which are very, very close to L, you take terms in the increasing order. Some of them, not all. I mean, first one doesn't say the order. All I said was, there are so many points very, very close to L. So, then you can pick one, then some term big, subscript bigger set. Like that it continues. So, that proof is very easy. However, there is some important fact here. If you take a limit point, it is a limit of a subsequence. any limit point is a limit of a subsequence. That's very important. In my books, I don't talk about the limits. But the truth is that every limit point is a subsequence of a limit point. Subsequence. I am talking nonsense. Every limit point is a limit of a subsequence. Right? The proof is also like what I said here. Then let's read remark 6.6.7. The above two propositions give a sharp contrast between the notion of a limit and that of a limit point. When the sequence has a limit, then all subsequences also converge to L. This is one of them. But when the sequence has L as a limit pointer, then only some subsequences converge to L. If the whole sequence converges to L, every subsequence converges to L. But if L is a limit point, there are some subsequences which converge to L. Okay, so we can now prove an important theorem in real analysis. If he says important, it must be very important. Due to Bernard Bolzano and Karl Weierstrass, these guys are German guys. German guys, I mean, we are having a hard time because of these Germans. No? Even the Second World War, because of Germans. Most of them have things done by Germans. Even today, German engineering is far superior to that of American or French, I don't know, Chinese, Japanese. So Germans are big shots in everything. It says every bounded sequence has a convergent subsequence. So this is a very, very important. Every bounded sequence, if you take a bounded sequence, guarantees that if you take a boy, every boy has a mother. Guaranteed. Mother may be dead, maybe she is in Dubai, it stays so. But regardless of that, every boy has a mother. Like that, every bounded sequence has a convergent subsequence. Very important one. I guess he is proving it. So, this is not how I proved it, but you are buying my books, no? I would like to spend 1 or 2 hours with my material, not in a rigorous way, but to tell you the truth about what I have written. Bolzano-Weierstrass theorem. So this is a very famous theorem, by the way. O-level geometry, Pythagoras theorem is very famous. Pythagoras from is actually after passing O-level, after clearing the O-level exam, till you go to your deathbed, the theorem you use is Pythagoras theorem from O-level. Other theorems you don't use, no, I don't know. But even in this course we are going to use Pythagoras theorem. So it is that important. Alright, like that Bolzano-Weierstrass theorem is, oh my gosh, very important. It's simple, however. What it says is, let A and B a bounded sequence, then there is at least one subsequence of A. Every bounded sequence has a convergent subsequence. So this is something you cannot forget. Even now I said it 3 times because frequency is got higher because it is important. Every bounded sequence has a convergent subsequence. Now before we go to the theorem, I want to say something else. Other thing is, every sequence in this world has a subsequence which has a limit. Did you see the difference? Karl Weierstrass says, Bolzano-Weierstrass theorem says, every bounded sequence has a convergent subsequence. That is, that subsequence has a limit, real number limit. It is a real number. Now what I am saying is, if you take any sequence, somebody writes, you are blindfolded, somebody covered your nose, I mean not the nose but the ears. Then he will say, I wrote a sequence on the board. He may ask, you are blindfolded, you cannot say, what can you say about the sequence? You can say right away, there is a subsequence which has a limit. You don't ask whether it is, if he says if it is bounded, you can say there is a subsequence which converges to some real number. But if he does not say anything other than A is a sequence, guaranteed that there is a subsequence which has a limit. They are amazing things. That's why I say analysis is so beautiful. That's why someday you may come to maths. Very beautiful, amazing. So, if it is bounded, sequence has a finite limit. If it is unbounded, what will happen? If it is unbounded above, sometimes go to heaven, it has a subsequence. Limit xn n tends to infinity is infinity. If it is bounded below, if it is unbounded below, then some terms get closer to hell. So that means there is a subsequence whose limit is minus infinity. But in analysis, this one is like the backbone of the analysis that we are going to learn. This is that important. Okay, I said it 2-3 times. Tea time is getting close. Let's start.